Picture distant galaxies as lanterns on a vast dark lake. In the late 1990s, two rival crews, one dubbed the Heisey Team, the other the Supernova Cosmology Project, watched for the moment a lantern flared and faded, a type Ia supernova, nature's near-perfect flashbulb, because every blast releases almost the same torrent of light. Its apparent brightness tells a simple tale. How far the lantern stands and, more subtly, how swiftly the lake between us has stretched during the light's long voyage. Night after night, the astronomers sifted curves of fading starlight, fitting each with clockmaker care. The results felt wrong at first blush, too dim for their redshifts, as though the universe had spirited them farther away than expected. One data set might be blamed on dust, two on calibration, but 24 supernovas sang the same off-key note. When the numbers settled, a stunning picture emerged. Cosmic expansion is speeding up. Galaxies are not coasting inertially after the Big Bang's shove. They are accelerating, as if some gentle but inexorable pressure swells every cubic centimeter of space. In an ocean where the oars should have stilled long ago, the water itself is still rowing. The discovery appended textbooks overnight, yet its essence is beautifully humble. By timing the flicker of dying stars, we learn that the cosmos keeps pressing the accelerator silently, everywhere, all at once. Long before the first star sparked, the newborn universe pulsed like a drum. Tons and baryons light and ordinary matter locked together in a scorching plasma, sent pressure waves racing outward at half the speed of light. For 380,000 years, the cosmos rang with these primordial notes, till temperatures cooled enough to let photons fly free. The waves froze in place, leaving a faint preference, matter slightly more likely to gather. 150 million parsecs apart than at other separations, billions of years later, those ripples remain. Baryonic acoustic oscillations. Stone ring patterns now expanded to grand cosmic scale. Modern surveys such as IBOS and the Dark Energy Spectroscopic Instrument trace millions of galaxies, revealing concentric shells in three-dimensional space. Fly through their data and you swoop past glittering clusters, spaced like tree rings on an unimaginable trunk. Because the original sound horizon is known from cosmic microwave measurements, each ring acts as a standard ruler. Compare its apparent size at different epochs, and you reconstruct how the cosmic lake has stretched. Without relying on supernova flashbulbs or any single method's biases, the verdict aligns. Expansion is not easing. It is quickening. Thus, the universe itself preserved an acoustic fossil, a baseline laid down when no ears yet existed. By reading that frozen music, we confirm the supernova's hint. Some pervasive, unseen influence, dark energy conducts the cosmic symphony, lengthening every bar as the melody unfolds. Starlight travels the cosmos with monk-like discipline, straight ahead at light speed, no complaints. Yet when that steadfast glow reaches our telescopes, its shapes betray a secret. Galaxies that should appear round arrive ever so slightly stretched, as though glimpsed through faintly rippling glass. This is weak gravitational lensing, a subtle warp caused by all the mass, luminous and dark, that the light encountered on its journey. Survey teams like KIDS in Europe and the Dark Energy Survey in Chile have mapped these tiny distortions across a quarter of the sky. They measure not individual arcs, but wholesale shear patterns. Statistical whispers that reveal how quickly cosmic structures grow. If gravity alone reigned, the web of clusters and filaments would tighten with familiar Newtonian vigor. But observations show that growth is languid, as though an unseen counterforce gently loosens the cosmic loom. Dark energy, by accelerating expansion, thins the gravitational glue, letting woven threads relax. Soon, the Vera Rubin Observatory's legacy survey of space and time will chart tens of billions of galaxies, slicing the universe into tomographic shells. Stacked together, these shells will paint a 4D movie of how dark energy dampens the formation of structure. In each frame, the message will persist. The universe is not merely expanding, it is being stretched. And even the paths of ancient photons, the faithful reporters of distant epochs, carry the imprint of that invisible pressure. Pull every atom, ion, and photon from a laboratory chamber, and intuition says nothing remains. Yet quantum field theory insists the vacuum still quivers with zero-point energy. Particles and antiparticles flickering into existence before annihilating in a breath. Tally that jitter with naive mathematics, and you obtain a vacuum energy density a lot larger than what cosmology allows, enough to rip the universe apart in its first heartbeat. Instead, we observe a value so gentle it took billions of years to reveal itself. Einstein introduced the cosmological constant lambda as a mathematical patch. Today, we reinterpret it as the measured energy density of the vacuum, approximately equals 6 times 10 to the power minus 29 grams per cubic centimeter. Why such a small positive number? And why does it begin to dominate cosmic dynamics right now, when stars, galaxies, and curious primates can notice? This cosmic coincidence unsettles theorists. An unguided lottery seems improbably kind. Some propose hidden symmetries that cancel most of the vacuum's fury. Others invoke the multiverse, where countless domains sample different lambda and observers naturally arise, only where acceleration is gentle. Neither answer feels entirely satisfying. The gulf between particle theory and cosmic measurement remains the largest known mismatch in physics. Our most humbling reminder that understanding nothing may be the hardest task of all. As we press on, alternative visions, rolling scalar fields, modified gravity, phantom energies, all vie to explain the paradox. But any successful theory must reckon with this whisper-quiet pressure pervading the void. A pressure ghostly enough to hide for eons, yet insistent enough to steer the destiny of every galaxy we see. What if dark energy is not a constant at all but a restless field? Call it quintessence. Rolling ever so slowly down a shallow potential set in the earliest instance of time. In this picture, the vacuum's pressure is tuned by an equation of state number, W. A cosmological constant fixes it at -1 exactly. Quintessence allows values slightly higher, perhaps -0.95, its influence waxing and waning as the field glides. Some clues already tease this possibility. Subtle tensions between early universe measurements of the cosmic microwave background and late-time supernova surveys hint that dark energy might have contributed a pinch more during the epoch when the first galaxies lit up. But the equation of state can drift lower too. Should W slip beneath -1, theorists speak of phantom energy. Pressure so negative it does more than accelerate expansion. It forces it to run away. In that grim arithmetic, the scale factor diverges to infinity in a finite time. The notorious Big Rip. Long before that final cataclysm, clusters would shrug apart. The Milky Way would unspool, planetary orbits would snap like overstretched springs, and in the last trillionths of a second, even nuclei would dissolve into lonely quarks. Current data place W tantalizingly close to the -1 boundary. But uncertainty leaves both serenity and doom on the table. For now, our telescopes keep watch, tracing how the field or constant whispers through the alignment of distant galaxies and the timing of supernova beacons. Hoping to see whether the cosmos is coasting on a gentle hillside or teetering at the edge of an existential cliff. Perhaps the culprit is not a new ingredient, but a flaw in the recipe for gravity. Replace Einstein's elegant tensor with a more Baroque cuisine, say function theories that let spacetime respond non-linearly to curvature, or DGP Bragnold models where gravity leaks into a higher dimension, and cosmic acceleration can emerge with no dark energy fluid at all. Such ideas, however, carry footprints. They alter how quickly structures grow. Galaxies might still drift apart at the observed pace. Yet the knots of dark matter binding them would thicken or thin at rates general relativity forbids. To expose those differences, astronomers measure redshift space distortions, the slight squashing or stretching of galaxy clusters along our line of sight caused by their peculiar motions. Surveys like BOSS, DESI, and soon Euclid chart millions of spectra, extracting a growth factor labeled F sigma 8. Deviations from the CDM prediction act as fingerprints of modified gravity. Meanwhile, peculiar velocity maps, radar guns for entire superclusters. Track flows toward massive attractors, offering an independent check. Even the quiet chirp of a neutron star merger helps. Standard sirens provide an expansion history free from cosmic distance ladders. Compare that to structure growth, and any mismatch suggests gravity plays by unfamiliar rules on the grandest scales. Theoretical contenders must also evade solar system tests, often invoking chameleon screening extra forces that hide in high-density regions yet emerge between galaxies. Thus, the cosmos serves as a sprawling laboratory, and every new survey tightens constraints around gravity's throat, whether dark energy is substance, geometry, or both. The coming decade will weigh its nature with precision undreamt by the stargazers of 1998, and the verdict will redraw our map of what motion, mass, and emptiness truly mean. At dawn on a July morning, the European Euclid telescope unfolded its sunshield and turned its wide 1.2-meter eye to the dark. Over 6 years, it will chart 2 billion galaxies, sketching a three-dimensional atlas 10 times deeper than any before. Each pinpointed galaxy is a marker on an expanding balloon. Together, they trace how dark energy stretches the rubber from redshift 0.1 to 2, when the universe was one-third its current age. Close behind comes NASA's Nancy Grace Roman Space Telescope, whose infrared camera will catch thousands of supernova light curves in a single stare, tying distant standard candles to Euclid's standard rulers. On the ground, the square-kilometer array will listen for hydrogen's 21-centimeter whisper across cosmic time, converting radio static into a billion voxel movie of large-scale structure, and then an entirely different messenger. When the spaceborne LISA interferometer opens in the 2030s, it will eavesdrop on massive black holes merging at redshifts far beyond any Cepheid or quasar. These standard sirens measure absolute distance because gravity waves carry their own luminosity tags. Compare that yardstick to the redshift of the host galaxy, and you gain another rung on the cosmic distance ladder. Free of astrophysical complexities, together candles, rulers, radio maps, and sirens form a symphonic crosscheck. If they all hum the same accelerating tune, Lambda may keep its crown. Should one instrument hit a discordant note, new physics will beckon. And the silent push, now called dark energy, may reveal its true, perhaps many-voiced name. Dark energy, whatever its essence, is not a distant abstraction. It reaches into every future plan. In 5 billion years, the sun will redden. Yet long before then, the cosmic event horizon will have crept so near that only our local group remains within sight. One by one, familiar constellations will melt into infrared ghosts, their light stretched beyond the grasp of human retinae or human sensors. For explorers and engineers, the challenge is practical. A starship launched today toward Andromeda would arrive to find its destination sliding away faster than any engine could chase. Pulsar timing navigation must fold dark energy terms into its algorithms. Laser-ranged beacons must compensate for a metric that subtly inflates while the signal is en route. Even the cadence of future calendars may adapt, marking cosmic years by how much the scale factor grows. Yet ambition is resilient. Concepts for fusion sails, beamed propulsion, and generation arcs already account for the long haul, plotting trajectories against an ever-steepening expansion curve. Some visions turn inward, vast O'Neill cylinders orbiting within the Milky Way's enduring halo, self-contained and content beneath an indigo sky empty of external galaxies. Others imagine data archives messages in bottles launched beyond the horizon now, trusting that some far epoch or parallel cosmos might one day reel them in. In Part 5, Eternal Drift and Human Ambition, we will ride alongside those imaginings. We will trace the probable fates of Voyager, exoplanet probes, and hypothetical light sails, asking how knowledge, culture, and curiosity might thrive in a universe where motion never ceases, but destinations slip forever away. Dark energy has set the ocean in motion. The next question is how we choose to sail it.